I'm going to speak about a topic that is near and dear to my heart, which is what is a galaxy? And so many of you sitting in this room, even all of the lay folks in this room, may be familiar with the question, what is a planet, that recently confronted astronomers and was recently brought before the International Astronomical Union. And as a result of the discussion, what is a planet, our friend Pluto got demoted and is now happier with its brethren as a minor planet. And this discussion, what is a planet, began because of the discoveries of new astronomical bodies that caused astronomers to have to confront this question. We needed to think physically about what it means to call something a planet and how planets form and what things we should group together. And so over the last 5 years, astronomers and cosmologists have also been forced to confront the question, what is a galaxy? Inspired by the discovery of previously unseen objects that have challenged traditional notions of star cluster and galaxy, some objects that I'll be showing you this evening. And so in order to talk about this question of what is a galaxy, in order to convince ourselves that it's not just a semantic question, it's actually a question of physics and learning about the physics of the universe, I'm going to go through 3 different topics. First, I'll talk a little bit about how we came to know our own Milky Way galaxy and what our notion of traditional galaxies is, so we're all on the same page with what we generally have historically considered to be a galaxy. And then I'll show you some of these new discoveries of invisible galaxies and highlight the way they challenge these traditional notions and talk about how we've been resolving these challenges to our understanding of what makes a galaxy. And then finally, after we have a sense of what a galaxy is, I'll highlight how computer simulations of galaxy formation are helping us understand not just what is a galaxy, but why is a galaxy, and do we understand how they came to be so? So I'm going to begin with this nice picture of the night sky that I got from NASA's Astronomy Picture of the Day, which really shows us the presence of the Milky Way on our own night sky. And even I don't typically think about it when I'm looking up, but every one of those stars in our night sky belongs to the Milky Way galaxy in which we live. They're just some of the hundreds of billions of stars that compose our galaxy. Yes?
Where is the location of the photo?
So this was taken in Australia near a place called Lock and Gorge, and I don't know where that is, but I wrote it down in my notes when I snagged the photo. So all these stars are the Milky Way galaxy. And the word galaxy itself comes from the Greek for the phrase Milky Band. I won't say that because I, like a typical American, can only speak American and I'm not good at pronouncing Greek. And Latin Via Lactea means Milky Way. And so these are the words historically used to refer to both our own galaxy and then galaxies in general. And so in 1610, Galileo got his hands on one of the first telescopes ever made. 1609 was the invention of the telescope. And it was just about the 400th anniversary of this when I started at Haverford. And that began my, honestly, first appreciation of some of this history of how our galaxy came to be understood. And in 1910, very quickly after observing the moon and the night sky, Galileo wrote of the Milky Way, "For the galaxy is nothing else than a congeries of innumerable stars distributed in clusters." And this seems like a very simple observation to us now. But at the time, it was pretty revolutionary. It wasn't just this Milky Band across our sky. When you peer with a telescope, you actually see, as you look closer and closer to this Milky Band, there are more and more stars that are showing us where the disk of our own galaxy is. And then Milky Way mapping took a significant step forward in the late 18th century when the Herschel siblings used a telescope to make the first large-scale map of the galaxy within which we lived. And this is what that map looked like. It's commonly seen in most of our intro-level astronomy textbooks, where this is where we are, and it's got sort of this jagged, irregular shape to it, right? There's gas and dust in that Milky Band that extinguishes the light from a lot of stars in our galaxy, making it hard to get an unbiased view of our neighborhood around the sun. And by the end of the 18th century, Charles Messier had compiled the first massive catalog of nebulae, of these fuzzy smudges in the sky, of things like Andromeda and the M31, M51 Whirlpool galaxy, which we can see now in these beautiful images obtained on digital cameras. At the time, we didn't observe them in quite such detail. But even though Messier had cataloged these objects in the late 18th century, no one knew at that time whether these objects were contained within our own galaxy or whether they were in fact their own independent island universes or their own distinct galaxies. And so it's really the case that it's been less than 100 years that we've known that there was any other galaxy outside of the Milky Way. The Milky Way was the entire universe before then. So right until the 16th century, our solar system was the universe. Until the early 20th century, the Milky Way was the whole universe. So it's been a massive revolution, thanks in some part to Edwin Hubble's observations in the 1920s, which demonstrated for the first time that these nebulae that Messier and others had cataloged were actually outside of the realm of our own Milky Way. Okay, so armed with this history lesson of how we first came to know our own galaxy and its extent, and of the presence of other galaxies, I want to go through a brief exercise to convince everyone in this room that you actually know quite a bit about the question, what is a galaxy? And I hope you will appreciate after I go through this, it is not just a silly, cheeky exercise. I'm actually demonstrating something about what is a galaxy. So I'm going to go through briefly a set of pictures, and I want you to audibly tell me if it's a galaxy or not. And there's no tricks, it's not a prank. I'm not like, oh, haha, that's not a galaxy, even though it totally looks like it. It's not that. It's just really look at it. Oh, yeah, that's a galaxy. You might not know why you think it's a galaxy, and that's fine. Okay. No. But isn't that a great picture of Saturn? It's so cool. Look, you can see the moon, 3 of the moons right there. They're making pictures taken by the Voyager satellite into an IMAX movie of Saturn, which is aside my point, but keep an eye out for it. The footage is unbelievable. There's flybys you can see on the internet now. Okay, not a galaxy, planet. Oop.
Yeah.
Galaxy.
Yeah.
Galaxy. Sorry. Achingly cute goat.
No.
That's Betelgeuse. Betelgeuse, a red star in our sky. We can see it with our naked eye. Yes, that's a galaxy. Okay. Yes, this is a galaxy. Good. And this one's even a little bit harder than the others. This is the Large Magellanic Cloud. This is a galaxy, but it's a dwarf galaxy. It's about 1/10 the luminosity, 1/10 of the amount of starlight of the other galaxies I just showed. And actually, even though we're most used to looking at galaxies like this, even if you don't think you look at galaxies, you know, like, okay, that's a galaxy. That's what comes to mind. But the vast majority of galaxies in the universe are actually dwarf galaxies. And this is the Large Magellanic Cloud, and this is NGC 205, which is about 1/50th of the luminosity, 1/50th of the stellar content of the Milky Way. And in that picture of Andromeda we saw earlier, you could actually see NGC 205 as one of the little galaxies that orbits around Andromeda. Yes?
Are the stars on the edges of the photograph from our own galaxy?
Very nice. So let's take a look at this photograph together. I want to highlight a couple of things about this photograph, actually, and that's one of them. And so we'll start there. So we can see very clearly the elliptical shape of light that's coming from this object. And there's quite a significant density of stars and starlight going out to the edges of this figure. And in this particular image, most of those stars, most of that light is associated with NGC 205. But a couple of slides from now I'll highlight when that ceases to be the case in other galaxies. And another thing that I want to highlight about this image is the fact that the color of the light we're seeing is fairly orangish red. And the color of this light is directly signifying something to us about the history of this galaxy, where the only stars, or the stars that are producing most of the light, are older stars. They're either low mass stars of low temperature, or they're medium mass stars of low temperature, but they're giant stars. That's where most of the light is coming from. When you have young stars, they aren't typically young stars. There are more massive stars in those stellar populations. They have hotter temperatures, and so their black body radiation is bluer. So you see blue light, you know stars are forming. You see red light, you know that galaxy has old stars in it. You know, even just in the set that I've already showed you of galaxies, where you're just like, oh yeah, those are all galaxies, those are all galaxies. They span a very wide range of properties. Even if we just go back again to stellar content, those galaxies spanned a range of well over a factor of 100 in how much starlight they contained. And so what made them all a galaxy? What did they have in common? They all had stars. They were spinning. The stars are moving around. The stars are gravitationally bound. But actually, until several years ago, the actual way that you would see an object and say that's a galaxy is exactly what you were applying And very famous astronomers have summarized the definition of galaxy very recently, and even on the internet, on chats about what is a galaxy, as I know a galaxy when I see it. Why do we have to talk about this? Semantic question, I know when I see it. Didn't you all just know it when you saw it? Okay, and I'll show you an even more specific illustration of how can you know it when you see it, if it's not just one of those big spiral things. And so here I have a picture of a star cluster and a picture of a galaxy, and they have the same amount of starlight, but they look very different to us, where the star cluster is much more centrally concentrated, it's much more dense. The physical size of that star cluster is smaller, the density of its stars is much higher, the average distance apart, whereas the galaxy is much more diffuse. Another property of star clusters, and it doesn't appear to our eye to be much of a difference with this galaxy, Leo 2. Another difference between star clusters and galaxies is that all of these old star clusters, the globular clusters, appear round. And so if you observe a couple hundred objects and they all appear round, well, that probably means they're all spherically symmetric. And so old star clusters generally appear to be spherically symmetric. Okay, so you have this difference in morphology. Well, that could be considered to be stamp collecting. Okay, you've got these things, they kind of look the same, and those things, they kind of look the same. So I know when I see it isn't necessarily a classification system that's helping us learn more about the universe, but it's a good start. And we'll get back to the physical underpinnings of this in a little bit. Okay, so now that we've sort of exhausted all the galaxies that look pretty normal and we can easily classify them, let's just step down the chain a few more steps into the really dwarfy galaxies that are really known to be the most numerous type of galaxy in the universe. And we step down again here and see Sextans B, which is about 1/300th of the Milky Way's luminosity. And this is a nice galaxy, it's in the local group, and it's cool, we see that this is a very different color than the NGC 205. There's a lot of young stars in this, they're hot, they're blue, they're burning their fuel up very quickly. And we see how the light is contained here, and as you look out to the edges of this image, a number of these stars are between us and the galaxy. They belong to the Milky Way. Leo 1, you may start to notice, right, all of these galaxies, many of these galaxies I'm showing are named after the constellation that they're in. So Leo 1 was the first Milky Way companion that was discovered in the direction of Leo. Leo 1, we see, it's 1/3000th of the Milky Way's luminosity. Still very obvious in this image. These spikes here, this is an image from a large sky survey taken at optical wavelengths. This is an artifact from a very bright star lurking off the edge of the image. All these stars here, these are stars in the Milky Way, some of them are galaxies, but the stars between us and Leo 1, and these stars belong to Leo 1. And it's nice, now that we're looking at these less luminous objects that are nearby, you can really start to see the granularity of the galaxy. And your eye can pick out individual dots of light, and your eye can appreciate that some of those dots appear bluer, and some of those dots appear redder. And you can imagine looking quantitatively at how bright are all the stars in this object, and how blue and red are all the stars in that object. And looking at that is one of the keys to us finding previously unseen galaxies. But I will continue to step down to Leo 2. Leo 2 here is only 1/15,000th of the Milky Way's luminosity. And again, many of these stars belong to the Milky Way. This bright red block right in the middle of Leo 2 is a star between us and the galaxy. It's not some cool energetic thing happening in the middle of Leo 2. It's just a coincidence. And here's the bottom of the barrel until the turn of the last century. Okay, Draco, 1/50,000th of the Milky Way's luminosity, was discovered in the 1950s. In visual searches of photographic plate data, which is very impressive to me. We look at this nice full-color digital image obtained in the Sloan Digital Sky Survey in the last decade. And it's, we can see it, but it's a little bit hard. And so if you're having trouble seeing the galaxy, take a look near the outskirts here and sort of mentally count up about how many stars there are per area. But then when you compare that to the more central parts of this image, you can see that there's more stars near the center of the image than near the edges. And that excess of stars is showing you the presence of the Draco Dwarf spheroidal galaxy. And for about 50 years, this was the least luminous galaxy known in the universe. And it's orbiting around the Milky Way at a distance of a few 100,000 light years. That doesn't mean that the least luminous galaxy in the universe is actually that close to the Milky Way. But these dwarf galaxies that have very few stars, we could not have found them if they were at greater distances. And so of the hundreds of billions of galaxies in the universe, we have only one, our home galaxy, around which we can search for these extreme examples of galaxy formation. And galaxies are not randomly distributed in the universe. I've been sort of saying, oh, they're around the Milky Way, they're around the Milky Way. We have a pretty good idea of the distribution of galaxies in our local neighborhood. And this nice graphic from a National Geographic article about a year ago shows this, where this bright blob is the Milky Way galaxy, here is Andromeda, and you can see that there are sets of galaxies clustered around them. So much like there are planets orbiting the sun, and the sun is one of hundreds of billions of stars that orbits the center of our Milky Way, each of the Milky Way and Andromeda larger galaxies have dozens of littler galaxies orbiting around us. And at the end of the 20th century, in 1999, there were a number of theoretical papers that asked the question, could there be more? Could there have been galaxies that have evaded detection until now? Because theory was predicting that significantly more galaxies should be orbiting things like the Milky Way than we had ever observed. And so at this point, I'm in graduate school, and University of Washington, where I went to graduate school, was a member of the Sloan Digital Sky Survey collaboration. And this project is done starting in the mid to late 90s on a 2.5-meter telescope in New Mexico on Apache Point. And this was the first massive digital survey done at optical wavelengths ever. And at this point, there are now 15,000 square degrees of sky. So over a third of the sky has been observed by the survey, and the data are all publicly available. Anyone sitting in this room who says, I want to see if there's more galaxies or more streams of stars or more cool things in the Sloan Digital Sky Survey, you can go to the website and get the data, and you can play with it yourself. And so this illustration here, look, M51, just shows some of the imaging data that was available as of a few years ago in the Sloan Digital Sky Survey. And so at the end of my grad studies, there were about 500 square degrees available, which is only about 1/100th of the sky. And today, as I said, there are more than 14,000 square degrees available, both of imaging and of the spectra of stars, measuring how quickly they're moving and what their chemical compositions are. And here's the website of the most recent data releases. There's even been a popular book written about the SDSS project, and Jim Gunn, the Princeton faculty member whose brainchild this was, along with a number of other folks that played a significant role both in the construction and in the implementation of the science of this project, really highlighting the incredible impact SDSS has had on our understanding of the universe. And the impact of SDSS goes beyond our astronomical understanding of the universe. This is one of the very first, if not the first, big data project. Big data is sort of a nice key slang word that we hear nowadays. The volume of data obtained in the first couple of years of the Sloan Digital Sky Survey exceeded the entire previous full volume of data obtained in all of ground-based astronomy before then. And I think there's 140 terabytes of data available to search on the SDSS website now. And so it's really led the way in terms of data acquisition analysis and how to efficiently serve it out to a public with a very broad range of interests. And so knowing that these data were coming out and knowing that there was this big question of, are there missing galaxies we haven't found yet? We embarked on a mission to, quite frankly, I wanted to quantify the galaxies that weren't there. I didn't think that we'd find any. I don't know why. I guess I was a pessimist. I thought, okay, we're going to use this data. We're not going to find anything, but we will quantify all the galaxies that don't exist. We will rule out their existence, and then I'm going to go do theory to explain why they're not there. But then, a couple years after I graduated and more data were available, we showed the existence of the first of these invisible objects. So there's a galaxy with 1/1,000,000th the Milky Way's luminosity in this image. And I can't give you a trick for how to see it. I know where it is. I can't see it in this image. There's no image that shows the presence of this galaxy that's 1/1,000,000th of the Milky Way's luminosity. But the way that we found it was, and this is a nice visual illustration, everything is automated, done statistically to take out the human bias that can go in to such visual evaluations. We didn't look at the actual pictures of the sky because you can't see the galaxies. But instead, we looked at lists of the positions and the brightnesses and the colors, how blue and red, are hundreds of millions of stars. And you can imagine, you just take a snapshot of the sky and you look at, well, where are the stars? One dot, one star. And you look at a little patch of sky, one dot, one star. You don't necessarily see anything. And then you can imagine saying, okay, well, I know more than where the star is. I know how blue and red it is, and I know how bright or dim it is. So I'm only going to look at where the stars are that have the right colors and brightnesses for possibly belonging to a little galaxy that I haven't seen before. And you can look at that spatial distribution, and you start to see a little blip is appearing. And then you can do some image processing and smooth the image and this and that. And we see that there's a very statistically significant blip in this image. And so when you run this automatically on thousands of square degrees of sky, all of your strongest blips, showing that there is some sort of an overdensity of stars with just the right colors and brightnesses, those all turned out to be invisible galaxies, now 5 years in. And so here's a revisit to that image that we couldn't see the galaxy in, and we still can't see the galaxy in it. But if I draw purple triangles around all the stars that have the colors and the brightnesses consistent with belonging to the invisible galaxy, okay, it's still not that convincing, but you can kind of see there's an overdensity of those sources sort of in here in the image. So you might be thinking, I'm not too sure about this invisible galaxy thing. So how is it that we can be certain? The two primary ways that astronomers have needed to confirm the presence of these galaxies is by going and getting a spectrum of every single one of these stars that's surrounded by a purple triangle. And when you take the spectrum of a star, you can measure how fast it's moving. You can measure what the chemical composition of the stars are. And you see, these stars are moving together. They're moving around a common center of mass. They're physically associated with each other, and they're moving together. You can use those kinetic energies also to weigh the galaxy. Another thing you do is you go and take a much, much, much deeper image than you discovered the galaxy in. And when you take that much, much, much deeper image, you can start to see, you can see the stars that belong to that galaxy. You can see that sequence in color and brightness space. That is the sort of smoking gun of the presence of a spatially coherent and temporally coeval population. In the same year, we discovered another object with 1/10,000,000th of the luminosity of the Milky Way. It's extraordinarily tiny. So this object in total, this galaxy, which has gotten me some notoriety in the field as it's now referred to as Willman 1, as actually being the first example of such objects in the universe, has only about 1,000 stars in it total. And if you add up all of the light from all of those stars, it is less luminosity than that star Betelgeuse emits by itself. So when we look up at our night sky, we see a very biased view of what stars look like. But most of those stars, single stars are emitting more light than this entire galaxy. And so since these two original discoveries, roughly a dozen more invisible galaxies have been found to orbit the Milky Way. And they are the darkest galaxies known anywhere in the universe. And by darkest, I don't just mean having the least light, which is one way to define darkest. I also mean that when you weigh the galaxies, that when you measure the kinetic energies of the stars, and you ask how much potential energy needs to be there to keep them gravitationally bound, that they have the highest amount of missing mass. It's like, gosh, if I add up all the mass from those stars, that's just a tiny fraction of what I need to explain the existence of these objects. They have the highest ratio of dark matter to stars of any galaxy known. And so I'm only going to show one figure here, and this is the figure, which summarizes the properties not just of the 15 newly discovered invisible galaxies around the Milky Way, but also the about 10 previously known dwarf galaxies around the Milky Way, and then the similar analogs around Andromeda. And the reason I want to show this image showing the physical sizes of these dwarfs compared to how luminous they are, how much starlight they have, from 1,000 times the amount of the light emitted by the sun to 10 million times the amount of light emitted by the sun. A big thing I want to drive home here is just the incredible range and properties among the tiny dwarfs orbiting the Milky Way. We have from 500 times the luminosity of the sun up to 10 million, and that's not even including the Magellanic Clouds. How can we call all of these the same? Is it meaningful to classify them all as galaxies? And so I will zoom out on this same figure to show you how I know it when I see it, how that galaxy definition has been able to persist for so long. And so what I've done in this zoom out is I have a similar range from 100 times the luminosity of the sun now to 1,000,000 times the light emitted from the sun now versus their physical size in light years. And these colored dots show where galaxies live, and these filled in dots show where star clusters live. And except for this one very unusual globular cluster, we see a significant separation in the physical sizes at a set amount of starlight. I know it when I see it. Those star clusters are just physically denser. However, when we look at these dimmer objects, these in here have only been discovered in the last 8 years. That's not quite a clean separation anymore. So even if we wanted to, we can no longer use I know it when I see it as an adequate definition. And so if you want a new definition, you can Google what is a galaxy, and you can see if that helps you at all. If you're an astronomer making a discovery, or let's say you're a theorist who's made a prediction. I've predicted how many galaxies there should be. Which objects should I be comparing my prediction to? And so Google tells you it's a system of millions or billions of stars. Okay, well, we already lost out on that. We have galaxies now that are thousands of stars, but fine. Together with the gas and dust, there's a bunch of galaxies that might not have gas and dust. Okay, that's fine. Held together by gravitational attraction. Okay, I'm on board with that. It needs to be gravitationally bound to be a galaxy. Right, we're seeing objects we can measure. Their stars are 10 billion years old. They wouldn't just be happening to pass by each other in space. Okay, but that's not great. What if we look at Wikipedia? Do we get a better definition of galaxy? It's pretty similar, but Wikipedia adds in this idea of dark matter, which I had mentioned seems to be a necessary component to explain the observed properties of dwarf galaxies. And we can be more serious about it. This was a monkey on my back for some years, actually. And so a colleague and I finally put this paper out last year called Galaxy Defined, and I learned a lot of things from writing this paper. One of them being, if you want people to take your paper seriously, do not use a cheeky title for the paper. But we thought really hard about this because there was a problem in the community. There is a problem in the community where there's a vocal minority of folks who do not like saying a galaxy is a gravitationally bound object with stars and dark matter. Because, dark matter is a theory, right? And there's a whole lot of evidence that we live in a universe with most of the mass in the form of dark matter. And I like that. I believe very much in that message that's giving us. But other people are still interested to pursue other options. And so that's fine. And so we suggest a modification of a galaxy is stars plus dark matter, whereas a galaxy is an object whose properties can't be explained by a combination of Newton's gravity and the observed mass that we see. So this is fine. So you can change your theory of gravity, or you can say that there needs to be dark matter there. And this is something that's been getting discussed a fair bit. And again, a way of simplifying this is star cluster, it weighs what you expect. Galaxy, you weigh it, there's something missing. And so it's quite interesting that this, I know it when I see it definition, even though it's seemingly ad hoc, it is the case that all objects defined as a galaxy, classified as a galaxy with that definition, also have dynamical evidence for dark matter. They have to have dark matter. All objects that have been previously classified as star clusters, none of them need some mysterious mass or some new force or some modification of gravity to define their properties. So without it being explicit, without us realizing it, there actually was a physical commonality linking all of these objects. And the same persists now. From that 500 solar mass and from that 500 solar luminosity galaxy all the way up to the ones with billions, hundreds of billions of solar masses, we need to have either dark matter or a modification of gravity to explain their properties. So what is dark matter? Okay, so it's a fundamental ingredient. It's of great importance to understanding galaxies. What is dark matter? Well, at the most basic level, dark matter is mass that's dark. This isn't really emitting its own electromagnetic radiation. I guess a little bit of black body radiation. But you could consider a rocky planet to be dark matter, this to be dark matter, black holes, dead stars. But in practice, we think that the vast majority of dark matter in the universe is some sort of a particle that particle physicists are still trying to figure out both theoretically and experimentally, a weakly interacting massive particle. But you know, the beauty of this from my point of view is, outrageously, it doesn't matter what the dark matter is. We don't need to know what it is to make detailed predictions for what the universe should look like if 90% of the mass is in the form of dark matter. All I need to say is, I need a hypothesis for how much there is, and I need to say that I also have a hypothesis that it interacts gravitationally. And if I do this, if I have my computer and I put in how much mass I think there is in the form of dark matter, and I distribute it the way I think mass was distributed very shortly after the Big Bang, thanks to observations of the cosmic microwave background, I add Newton's laws of gravity and I press go and wait for 13.7 virtual billion years. And then I can look and see, well, where's all the matter in the universe? And this image here is showing us one such prediction for how we think matter should be distributed around a galaxy like the Milky Way. And so what we see here are all of these splotches of light. Each one of these distinct splotches of light that your eye can pick out is a self-bound, it's a distinct clump of dark matter. In the very center here is where we think a galaxy like the Milky Way would live. And this is about the rough relative physical scales. We look at those big, beautiful pictures of galaxies, and those are just a tiny fraction of the full volume of what's going on. All the action I'm interested in, actually, occurs far outside that visible disk of the galaxy. And that's where a lot of the exciting dark matter action is as well. And so if you're an astrophysicist that wants to learn about how much dark matter there is, what are its properties, how is it distributed, that's the neighborhood that you want to look in. And so this is great. We have seen 25 dwarf galaxies around the Milky Way. We think they need dark matter to explain their properties. So 25 of these dark matter halos are lit up by dwarf galaxies. But the cutting edge research now is trying to understand, why are only 25 of the dark matter halos lit up by dwarf galaxies? Is that a problem with our model? Have we just not found the dwarf galaxies yet? Or are there additional physics that explains why the vast majority of these predicted overdensities of dark matter, why they're empty? Are there really tens of thousands to hundreds of thousands or more clumps of dark matter orbiting around our galaxy that we can't see, that are virtually invisible to us? So that's one of the things that I've been focusing a lot of my research on now. Nevertheless, there's broad agreement within the community of what a galaxy is. It is something lighting up one of those dark matter halos. And so that now we've described what is a galaxy, do we understand why that is? Do we understand in detail how those galaxies form stars inside of them? What happens to the gas? And how does the galaxy change over time? And so a way that we can do that is step away from our simulations that only include dark matter and gravity and start adding other ingredients and other physics, such as gas. We can add in hydrodynamics. What happens to gas? How does gas cool? How do stars form out of cool gas? What happens when a supernova goes off? Where does the gas go? And what does it leave behind? And then you need a supercomputer. This takes a lot of time to crunch. So sometimes simulations like these might take millions of node hours on a computer. And you run many CPUs at one time, because it's a lot of hours, is a million. And you can run this. And at the end, you can get out a simulated galaxy. And really, right, a simulated galaxy, it's a list of numbers. But you can take those numbers and you can emulate observations and then see how much simulated galaxies look like real ones. And then turn some of the knobs to say, well, which physics is really controlling the properties of galaxies? And how can we use that to understand better? And a colleague of mine, Andrew Ponson, has made a very nice, just 1.5 minute long animation that talks a little bit about what a galaxy simulation is and how they use it. And it's just sort of a fun, silly thing, but I like showing it because it summarizes better in 1.5 minutes than I would be able to.
This is a galaxy. Okay, so it's not a real galaxy. For one thing, we can't do this with real galaxies. No, galaxies are too big to fly through. This is a digital galaxy. A digital galaxy really looks like this. Vast numbers of numbers detail the distribution of mass in the Big Bang of a virtual universe. A computer uses the laws of physics to evolve the universe through time. Here is the dark matter, which is best known for being dark. But in the virtual world, anything can be eliminated. Dark matter can be green, if you like green, which I do. The visible universe looks more like this. Well, actually, that's a bit of a cheat too. We're taking virtual pictures of the gas, the stars, and the gas that's turning into new stars, giving them any colour we like, then combining the layers. But it's not too much of a cheat. Pictures of real galaxies are often coloured in this way too. Wait a few billion years in the real universe, or a few hundred years for a computer, or a few months if you've got a supercomputer, and then you have a galaxy. Well, you could have just looked at the sky, but we still make virtual galaxies because they help us study where the real galaxies came from.
Okay, cool. So on the next slide, I show a little montage of simulated galaxies embedded in an image with real galaxies. Okay, so this is the second and final quiz of the talk. So take a look, and I know it's a big room, small screen. Can you pick out, even if you just focus on one or two, what is a real galaxy, as in actually observed in a digital image, and what is a simulated galaxy that has been processed to make a fake image? You may talk to your neighbor if you want. About astronomy in this image. As you guys laugh, the screen shakes more. Isn't that weird? It's like just the sound waves. I will soon spoil the surprise and label them. Okay, are you ready to have the surprise spoiled? I forget. R means real. If it doesn't have an R next to it, it's a simulated galaxy. I actually need to cheat sometimes. It's hard to get them all. And so one of the ways, especially if you're looking really closely at the image, the way that I'm able to figure out which one's real or not is a big limitation of the simulations is the spatial resolution. And so the simulated galaxies look a little bit smoother when you look close up. You can see more fine spatial detail in the real galaxies. And so we sure have not solved the problem of galaxy formation. Oh, it all fits fine. Yes, we live in a cold, dark matter universe, and you throw in all these laws of physics, and we predict what all the galaxies look like. That is not the case at all. There are still huge gaps in our understanding of how galaxies form, and there may well, down the line, be shown to be problems with our idea that most of the universe is cold, dark matter and dark energy. However, we've progressed to the point where qualitatively, we make galaxies that look pretty much like real ones, which is amazing. We're just people. We're just people. It's so humbling, right? The universe is so big and we're so small. If my head was the sun, the next star, let's see, what state are we in, Nebraska? The next star would be, in the Atlantic Ocean somewhere. Right? Stars are really far apart. Space is empty. Yet we're able to take our knowledge of physics as we figure it out here on Earth, simulate stuff with dark matter that we don't even know what it is, and produce these incredibly big and beautiful galaxies in some detail that accurately reflects what we see in the universe. And hopefully the fact that there are so many open questions yet to be answered. I always want that to inspire some possible future scientists who are listening to this. Like, dude, there's so much stuff that people don't know yet, and there's definitely a role for you in astrophysics to figure some of this stuff out. And so what's the future? There's a lot in the future. This really just sums it up in a couple sentences. I leave a lot out here. So I'm very involved in something called the Large Synoptic Survey Telescope, which has been identified as the biggest ground-based mission in U.S. astronomy that's supposed to be happening and starting over the next decade. And so this is a telescope. Ground has been broken in the southern hemisphere for this 6-meter class telescope that's going to image half of the sky over 1,000 times. To not only create the deepest wide field image of the sky ever made, but to make a movie of that sky and how it changes over a 10-year period. There will be many petabytes of data obtained for the LSST project, a huge amount of data, so also very exciting for statisticians and computer scientists and data analysts, engineers, astronomers. It's this very cross-disciplinary science project. With this and other surveys, I and others are excited to search for more invisible galaxies. It's cool that we found about 12 or 15, but it may be the fact that invisible galaxies are the very most numerous type of galaxy in the entire universe, which is bananas to think about. We didn't know they existed until a few years ago. They might be the most numerous type of galaxy. They might not contribute very much to the total number of stars in the galaxy, but we think that galaxies formed from small things merging to form big things. And so these could be much like the building blocks of larger galaxies. And the fact that they're low mass and that they have relatively shallow gravitational wells makes them very sensitive test beds for the sort of physics that affects galaxy formation on all scales. Okay, so searching for more and getting a more unbiased understanding of the demographics of how these galaxies form and exist is very important. And also, galaxy simulations are always improving to help us learn better what dwarf galaxies may or may not reveal about dark matter. Are invisible galaxies the holy grail for understanding dark matter? That's yet to be seen. But an awesome thing is that somewhat in thanks to invisible galaxies, past efforts to bring particle physicists and astronomers to be closer together have started to prove fruitful, because people are doing things like looking for gamma ray signals from annihilating dark matter, which may live at the centers of some of these dwarf galaxies. So who knows what will happen with that? And so finally, I'm sorry, I'm lame, I'm not on the internet here, so I didn't bring up any of these websites. What if you're like, oh my gosh, I just realized my destiny is to study galaxies or to study invisible galaxies, or even if you just want to dip your toe in the water. Like, there are many online resources to learn cool stuff about physics and astronomy. But one way that astronomy has been particularly outstanding is bringing research data, not just research like, actual data that people are discovering things in, very friendly to the public and very well served out to the public. Things like Galaxy Zoo and other projects within the Zooniverse. If you just Google Zooniverse, you'll find all of this Galaxy Zoo stuff. There have been many, many dozens of peer-reviewed papers coming out of the Galaxy Zoo project. My students love doing it. You go and you actually classify galaxies with your eye. There's a tutorial for how to do it. You don't need to worry about messing up because many, many thousands of other folks are doing it, and it kind of averages out. And astronomers are learning things that are otherwise unknowable based on everyone's joint classification. This crowdsourcing of galaxy classification is very important because galaxies, as you've seen just from this little sample, they span an unbelievable range of properties, and there's only so much you can train a computer to do without going down to the human eye sometimes. There are a number of really super duper cool interactive Milky Way tutorials, and I should have, instead of writing interactive Milky Way, written down the word chromoscope here, because chromoscope has from gamma ray all the way to radio wavelengths. You can slide through what the Milky Way looks like at all these different wavelengths and zoom in and out and scroll all around. There's also a 1 billion star interactive map of the Milky Way. Google 1 billion star Milky Way map near infrared. It is amazing. You can actually zoom in all the way and pan around and see star clusters and all of these. Well, you couldn't count all the billion stars. It would take a very long time, which is pretty cool. And as I said, the Sloan Digital Sky Survey itself, the data are very friendly to the public. I have my students write SQL queries to go into the database, but you can actually just go online and click. There's some nice graphical user interfaces to get the data that you want. And if you're interested to learn more about any of these things, my email is easy to find on the internet. I'm Beth Willman. You're free to send me an email. I'd be happy to send you more links for how to interact with these things. And I think my next slide is the end. Yeah. So thank you very much, and I'm happy to take any questions. Sir.
Does the distribution of masses or luminosities obey any simple statistical formula?
Okay, good. So the question is there some sort of a statistical formula or fitting function that can do a good job describing the mass or the luminosity distribution? So there are a couple of different ways that astronomers want to know the answer to this, because if you can write down an equation that describes the relationship between different things, that's something that's relatively straightforward to test with a prediction. So we don't actually have an unbiased enough sample of invisible galaxies to know whether they fit. So there's a Schechter function, something that gives you the number of galaxies as a function of their luminosity. We still don't empirically know the answer to that question. As far as what the density distribution is either within an individual galaxy or as far as what their actual spatial distribution is, we're also still trying to answer those questions ourselves. We expect that the spatial distribution of galaxies, for example, how many there are as a function of distance from the Milky Way, we expect that that density is proportional to 1 over r squared, 1 over distance squared. And so we can play games, like right now, my postdoc is assuming that's the spatial density distribution, and then predicting how many galaxies we should find if that's true. Yes, please.
Most of the larger galaxies have supermassive black holes at the center. Have you found any supermassive black hole indications in any of these very small galaxies?
So I'll say why the answer is no, and then I'll say where my ignorance starts to step in. And every time someone asks that, I'm like, oh, I'm going to calculate that number. So there is no evidence for a supermassive black hole in any of the Milky Way's dwarf spheroidal galaxies, even the ones that are more like 1 million solar luminosities. However, we couldn't see the evidence if it was there the same way we can see it in the center of our own galaxy. In the Milky Way, there's a whole bunch of stars around the black hole that are really close to the black hole. And so we can measure how fast they're moving. Actually, hopefully as I speak, I have some students back home doing this. It's their project that they're working on now. And we can use different mass estimators to show that there needs to be a black hole there. But the density in these dwarf galaxies isn't high enough to unambiguously show that you need to have a black hole amount of mass within the size that you need. The thing that I always think to myself, oh, and I wish I had that number, is that we do observe relationships for more massive galaxies between the mass of the galaxy and the mass of the black hole. And then I was like, well, what would the mass of the black hole be in one of these? It'd be very, very small, but I don't know how small it would be. Please.
One comment on that, and then a question for you. It's been done with globular clusters,
yes.
So we know that there are actually black holes in the center of a lot of the globular clusters, which ties into the question.
Although I think
anyway,
that word "a lot" is quite controversial.
Well, Carl Gephardt's got his papers seem pretty sound.
So
yeah, it's definitely not a finished question, but there's a couple that are pretty strong cases. The globular cluster tie-in, so you compare and contrast there. Some years where you're getting close there, particularly like say Omega Cent, there's a lot of evidence or suggestion certainly that they've come in. A large portion of our globular clusters have always been hard to explain. Maybe the remnants of disrupted dwarf galaxies. So what does your work say on that?
Yeah, so there's about 150, to put Lee's question in context, there are about 150 of these globular clusters, these old star clusters known orbiting around the Milky Way. And of those 150, I would say there's only about 4 that have stellar populations that are a bit different than than the other globular clusters. And so the vast majority of globular clusters, it appears as if all the stars formed at the same time, and that there's no difference in their iron abundances from star to star. Why is iron special? Well, you need a supernova to make iron. Okay, and so if you have no spread in your iron abundances, then maybe you pretty much formed all your stars at the same time. There wasn't a supernova that made iron that you then made future generations of stars out of. If you have differences in the iron abundances of different stars, you necessarily had to have a supernova going off, keep that gas, and then to form future generations of stars. And so it is the case that except for one globular cluster, all the globs with star-to-star variations in iron have deep enough potential wells to hold onto a supernova ejecta. So you don't necessarily need dark matter to explain them. And there's one, I forget the name, that was recently published to have iron abundances based on iron lines. It had star-to-star variation, and its mass is only about a few 100,000 solar masses, and its size is such that it couldn't have, but maybe it was stripped down. And I remain agnostic. I remain agnostic on Omega Cent. It has a very complex stellar population, so I think that may have been the strip core, but there's almost no way to know. I'm really excited about G1 around M31 and what follow-up observations might yield with respect to that. Please.
I have a question. So you started out by saying that astronomers know a galaxy in the Milky Way. That sounds like selection bias, but exciting new project Galaxies do. We teach amateurs to know it when they see it.
Yes.
Where's the science in that? And of course, that wouldn't have spotted the galaxies you did.
Oh, of course not. And because, well, they're given galaxies that are already known to be there. And so in Galaxy Zoo, people aren't asked whether it's a galaxy. It's already been determined to be a galaxy based on, quite frankly, I know it when I see it. These things look, by some metrics, similar to the things that have been seen before. For example, by adding up the total amount of brightness in the image and then the physical extent of that image. And, on one hand, you might think, oh, well, you could be missing something different. Maybe there is some weird object out there. And so that's where future unexpected discoveries, these serendipitous discoveries can come in. But we can only work with what we know, and we know that, well, all those things that have about that much brightness, that have about those physical sizes, all those things have been confirmed to be physically galaxies by the fact that their dynamics need dark matter to explain their existence. So, and even in our, galaxy defined paper, we propose diagnostics. They're different than those, but they also depend on a very limited understanding, quite frankly, of the universe.
But it seems like a dynamical definition is more reliable, perhaps, than a luminosity distribution definition.
Oh, well, of course in practice, right? But it's cheap to get an image, and if you've never seen an example to the contrary, you stick with it. You stick with what you can get for cheap. And we have spectroscopy of millions of galaxies now with SDSS. Cool. Okay, great. Thank you, everyone, so much for your time. Did you have to say anything, any thanks or closing words? No. Okay, great. Thank you.